So continuing our discussion of L'Hopital's rule and indeterminate forms, we have a few more situations that I want to talk about. One's where L'Hopital's rule applies even though it may not be immediately obvious. And that's kind of what we have going on here. Not only do we not have a quotient, we don't even have a product like we had in the last couple of examples we looked at in the last lecture. But let's see what we can do here. I'm going to do what we usually do with the first, just try the obvious thing. If you just try substituting pi over 2, secant of pi over 2 is undefined, tangent of pi over 2 is undefined, or they're both infinity. So that doesn't work. All right. So here's what I'm going to do. I'm going to do the thing we usually do with trig functions when we're at an impasse and we want to clean it and we want to try to find a path forward. I'm going to rewrite them in terms of sine and cosine. All right. So this becomes the limit x approaches pi over 2 from the right of 1 over the cosine of x minus the sine over the cosine. Well, okay, that looks promising, right? The denominators are already the same. So let's go ahead and combine them together, make it a single fraction. This is the limit x approaches pi over 2 from the right, 1 minus the sine of x over the cosine of x. And now we have the L'Hopital's rule situation. If you try substituting pi over 2 in the numerator, it's 1 minus 1, that's 0. Substitute it into the denominator, cosine of pi over 2 is 0. Excellent. So pi L'Hopital's rule. Differentiate the top and the bottom. This is the limit x approaches pi over 2 from the right of 1 minus the cosine of x over minus sine of x. Okay, so what happens now? If we try to put pi over 2 in there, right, this is 1 minus cosine pi over 2 over sine pi over 2. That's, let's do your trig functions, right? 1 minus 0 over 1. The answer is 1. There we go, it works. We had to work with it a little bit, right? But we were able to come up with the answer. You notice what's going on in the original function, right? We have yet another situation where both functions are going to infinity, but they're doing it in kind of a consistent way. So that they're doing it kind of at the same rate. So when you take the difference, right, you end up being kind of the difference of those consistent rates, which are constant, and you end up with a number. Okay, so how about this thing? X to the x power. Okay, well, you put 0 in there, right? We always kind of try direct substitution first. This becomes 0 to the 0 power, and that does not help because that's undefined. All right, so here's how I'm going to do this. I'm going to take a little twist. I could, in theory, do everything I'm going to do just with the limit the way it is, but you have to do this weird e to the ln of, so it gets a little strange. All right, so what I'm going to do is I'm going to say, look, let y equal x to the x. All right, then I'm going to take the logarithm of both sides. The log of y equals the log of x to the x. All right, now let's simplify that logarithm, the right-hand logarithm. Let's make this the log of y equals x times the log of x. All right, and that's looking a little more promising. Now let's take the limit of both sides. The limit x approaches 0 of the log of y equals the limit as x approaches 0 of, whoops, got ahead of myself, x times the log of x. Okay, now if you try putting 0 into that right-hand side, what do you get? Well, this becomes 0 times infinity, which technically isn't an indeterminate form. But look, here's what I'm going to do. I'm going to rewrite this. I'm going to make this the limit x approaches 0 of the log of x over 1 minus x. Right, take a second, right? Confirm for yourself that do the thing we do, right? Keep the numerator the same, change the division of multiplication, flip the denominator, right? You try simplifying that. It does equal the original. And now if you try substituting 0, this becomes infinity over infinity. That's an indeterminate form. Now L'Hopital's rule applies. All right, so let's differentiate. Derivative of the still the limit as x approaches 0. Derivative of the log of x is 1 over x. Derivative of 1 over x. X to the negative first. So this is negative 1 over x to the second. What does this simplify to? This is the limit x approaches 0 of negative x. And that limit is just 0. Okay, now be careful though. That's not the answer. Right? Remember, I wasn't working with y anymore. I was working with the log of y. But that's okay. Look, I can fix this. Here's what I'm going to do. I'm going to apply one of my limit rules. I'm going to bring that limit inside the logarithm function. This is the limit, the log of the limit as x approaches 0 of y equals 0. Okay, now convert this to an exponential equation. Right, convert this to the equivalent exponential form. E to the 0 equals the limit x approaches 0 of y. All right, but now remember what y is. Y is x to the x. So this is the limit x approaches 0 of x to the x equals e to the 0, which is 1. And that's it. There's our answer. Right? We just had to do this weird little trick. But remember, if you think back to when you first learned about logarithms, and you use them to solve equations like 5 equals 3 to the x. And the thing the logarithms really brought to that table was they gave you a way to get the variable out of the exponent. Well, I used it for the exact same purpose here, right? I had this feeling that my life was going to be easier if I could get that x out of the exponent, and taking the logarithm of both sides was what allowed me to do that. That's kind of I hate to talk about tricks because there are no tricks in math, but it's a technique that you should kind of have in the back of your mind. Anytime you have a problem with an exponent, one option, one tool you have is taking a logarithm and seeing if that lets you simplify it. Okay, so take a look at this one. Right, pause. Right, see what you can come up with. Then start it up and we'll go over it together. All right, so you see we've got a similar situation. If I just substitute 0, I get 0 to the 0 power. So I'm gonna try my same trick. I'm gonna say, look, let y equal x sine of x. Take the logarithm of both sides. Log of y equals log of x to the sine of x, and then use our logarithm properties. Bring that sine of x out in front. Okay, now take the limit. The limit x approaches 0 of the log of y equals the limit x approaches 0 sine of x times the log of x. And now we have that same situation we saw before. If you try substituting 0, sine of 0 is 0, limit of the log of x is infinity. 0 times infinity is kind of that pseudo indeterminate form. Right? I can make this into an indeterminate form by rewriting it as the log of x over 1 over the sine of x, which is the limit x approaches 0 log of x over cosecant of x. And now, if we take the limit of the top and the bottom, the numerator is infinity, the denominator is infinity, and now it truly is an indeterminate form. Okay, so let's apply L'Hopital's rule, right? The limit x approaches 0 of the log of y equals the limit x approaches 0, 1 over x over negative cosecant x times cotangent of x. Now, This does not appear to have resolved, at least not yet. I have infinity on the top and still infinity on the bottom. Okay, so it's still a L'Hopital's rule situation, still an indeterminate form, but instead of just I don't want to differentiate again. I don't want to try to apply L'Hopital's rule again, because if I do, I'm going to have to differentiate that cosecant of x, which is still going to give me a cosecant, and I'm going to have to differentiate that cotangent, which is negative cosecant squared, and the cosecants aren't going away. And really, that's what I need, is for the cosecants to go away. Okay, so instead, I'm going to apply kind of our classic trigonometry technique. I'm going to leave this the limit x approaches 0, 1 over x over cosecant is 1 over the sine. Cotangent is cosine over sine. Take that negative sign. Let's bring that negative sign out in front. Okay, so what is this then? This is negative limit x approaches 0, 1 over x over cosine x over sine squared x. All right, and that is negative limit x approaches 0, sine squared x over x cosine of x. Okay, now what? If we put 0 in there, right, try just direct substitution, we get 0 over 0. So this is once again looking like an indeterminate form. So now I'm going to apply L'Hopital's rule again, and this is equal to negative limit x approaches 0. It's a chain rule situation in the numerator. This is 2 sine of x times the derivative of the sine of x, which is the cosine of x, over, and then down here I've got a product rule. The derivative of x is 1, so this is 1 times the cosine, and the derivative of cosine is minus sine, so this is minus x sine of x. And now I think I'm okay. If I put 0 in here, this is negative 2 sine of 0 times the cosine of 0 over the cosine of 0 minus 0 times the sine of 0, and this actually cleans up nicely. The numerator is 0. The denominator, cosine of 0 is 1. 0 times the sine of 0 is 0. So this is just 1. And I end up with 0. But we're not done. Don't lose track, right? Don't lose track. This is not y. This is the limit as x approaches 0 of the log of y. So I still have to do that step where I undo this, right? Make this, and I'm really out of room. I'm going to have to squeeze in here up at the top. Make this the log of the limit as x approaches 0 of y equals 0. Now convert this to an exponential equation, the exponential version. E to the 0 equals the limit x approaches 0 of y. Y is just my original function, x to the sine of x. So the limit x approaches 0, x sine of x equals e to the 0, which is 1. That's going to be our final answer. So where are we going next? Now we're going to look at another application of derivatives. We're going to look at methods for finding the exact location of the maximum and minimum values of a function.